Alrighty, chapter 50. 14 chapters left of this book. I need to get my Git repo here cleaned up. Git status, git add, chapter 49. Git status. Yeah, we just did that one cat example with memory mapping. So let's go into README. We're going to mark off chapter 49 as complete. Bring that up here. And then we'll start on chapter 50. Virtual memory operations. Okay. Boom, boom, boom. Looks good to me. Git status, git add, readme. Git status, git DC. Cool. It is kind of awesome how terse some of the C stuff can be. The amount of capability you have versus the amount of code you have to write. It is quite amazing. I know some people might think, oh, a language like Python or something, you can do a lot more. You can express a lot more with fewer characters. But with language like Python, you just, or really any high-level language, you don't really have as much of a control over what's going on in the layers beneath your code. Especially with a language like Python, because you're going through like a virtual machine. Your code's getting compiled into bytecode that then gets interpreted by a bytecode interpreter, and then it's then running in this Python virtual machine, which is then mapping those opcodes onto functions that it has implemented inside the virtual machine that then actually run on the CPU. It's like so many layers removed from what is actually running on the CPU. Whereas these C programs, like, you're talking directly to the kernel. I mean, granted, the kernel is doing a lot of work for you to give these really powerful extractions, but it is beautiful. It is amazing and beautiful how much C expressiveness C gives you, and without compromising on having control over what the computer is actually doing. Like, if I didn't want to use these header files, like, I could just write, I can write my own C, my own style of C that does syscalls directly to the kernel without using any of the headers, without having libc, without having any dynamic linking, without any of that complex machinery. I could still write a program using C that talks directly to the kernel, and it wouldn't be all too much code compared to like doing it in assembler or something. So you get the control over assembler. You can literally write assembler in C, so you get the absolute control if you want it, and you also get this expressive power, this high level expressive power that I feel like most people don't appreciate. Granted, there aren't a lot of guardrails. That is the big failure of C, is that there's just, I mean, it's not memory safe, it's not type safe. There's a lot of ways that you can shoot yourself in the foot. And I think that's probably why most people fear C or have some anxiety around using C. But to be honest, I would not use C in a corporate environment unless it was like a specific library or something that a very talented, skilled team was maintaining. I wouldn't want an average developer off the street to start smacking the keyboard, and especially AI, using AI to generate stuff. I don't want them using a language like C, because they'll just end up shooting themselves in the foot. And a language like Rust, or a language like even Go for that matter, but Rust especially, Rust still gives you a level of control and power, but they have that level of safety as well that they provide, and type safety, memory safety. So yeah, I guess C isn't the be all end all, obviously, but it really is. It hits a sweet spot that I really think is powerful. And I think if you really want to understand operating systems and understand compilers, I feel like C is really the place you got to start. You know, there's just so much here. Well, I'm happy that I'm here doing C with y'all. So yeah, let's get into it here. Let me make this commit real fast. Sorry, that was like a random thought that occurred to me recently. Finish reading chapter 49. Go and push that. Why not? Okay, clear. So we're going to say 39. I'm going to start there on 1045. And this chapter is virtual memory operations. And obviously, you know, I can see from the first page here, it's stuff like mprotect. So locking the protection bits. I imagine that's going to be this type of stuff that we talk about here. Cool. So let's get started. This chapter looks at various system calls that perform operations on a process of virtual address space. So mprotect, system call changes the protection on a region of virtual memory. So we touched on protection bits in the previous chapters. Mlock and mlock, all system calls lock a region of virtual memory into physical memory, thus preventing it from being swapped out. Mincore, memory in core system call, allows a process to determine whether a page in a region of virtual memory is resident in physical memory. So how is that different from locking? So locking locks a region of virtual memory into physical memory, preventing it from being swapped out. Mincore system call allows a process to determine whether the pages in a region of virtual memory are, so it allows you to read whether it's resident or not. Okay. Madvise system call allows a process to advise the kernel about its future patterns of usage of a virtual memory region. So you're telling the kernel, hey, you know, this is how I plan on using this region of memory. Give you some hints so that we can get maximum performance. Some of these system calls find particular use in conjunction with shared memory regions, but they can be applied to any region of process's virtual memory. The techniques described in this chapter are not, in fact, about IPC at all, but we include them in this part of the book because they are sometimes used with shared memory. Changing memory protection, mprotect. The mprotect system call changes the protection on a virtual memory page. The protection on virtual memory pages in a range starting at adder and continuing for length bytes. Mprotect. So we give it an address, we give the length, and we give it the protection bits. So I guess it's like a set. The value given an adder must be a multiple of system page size as returned by the page size sysconf. Substitute specified adder must be page aligned. Sys4 says that implementation may require it to be aligned. Because protections are set on whole pages, the length is in effect rounded up to the next multiple of system page size. The protection argument is a bit mask specifying the new protection for this region of memory. It must be specified as either prot none or in combination created by oring together one of the more the prot read, write, and exec. All of these values have the same meaning as for mmap. If a process attempts to access a region of memory in a manner that violates memory protection, the kernel generates a sigseg v signal for the process. One use of mprotect is to change the protection of a region of memory mapped One use of mprotect is to change the protection of a region of memory mapped memory. What? I kept on switching those words. A region of mapped memory originally set in the call to mmap. As shown in listing 51, this program creates an anonymous mapping that initially has all access denied. The program then changes the protection on the region to read plus write before and after making the change. The program uses system, I hate that function, the system function, to execute a shell command that displays the line from the procpid maps file corresponding to the mapped region, so that we can see the change in memory protection. We could have obtained the mapping information by directly parsing proc self maps, but we use the call to system, I should say, because it results in a shorter program. When we run this program, we see the following. So we run mprotect. Before mprotect, it has no bits, and then after mprotect, it has the read-write bits set. From the last line of the output, we can see that mprotect has changed the permissions of the memory region to prot read and write. For an explanation of deleted string that appears in dev0, yeah, we already talked about that in the previous chapter. Because it's not shared, it is effectively considered like a deleted file, because there's no backing to it. There's no file on disk for it. At least that's the way it's treated internally. Changing memory protection with mprotect. So we have, let's read through this program. We just pound define length to be a meg. Give me 1 second. All right. All right, so we pound define the length to be 1 meg. We define a shell format. This is really bad because it's a shell injection vulnerability type thing. I guess it's limited to be a long, so that's good. And it's probably not based on user input, so it's probably safe. I just really hate doing stuff like this. Command size of shell format plus 20. Very hand wavy. And the main, we allocate some memory for the command. We declare a char pointer to an adder. That gets returned from mmap. So we do our mmap up front where we say, hey, you got no bits. And then we do our system call here. And then we call mprotect again. Or sorry, we call mprotect setting these bits here. And then after the mprotect, we then run system again. And that displays the bits are set. Pretty straightforward. Memory locking, mlock in, mlock all. In some applications, it's useful to lock part or all of a process's virtual memory so that it is guaranteed to always be in physical memory. One reason for doing this is to improve performance. Access to locked pages are guaranteed never to be delayed by page fault. This is useful for applications that must ensure rapid response times. What I've seen in previous environments that I worked in, that they would just not have any swap space. They would just disable swapping altogether. And I think that pretty much effectively does what mlock is doing, just for the entire computer. Let's ask AI that. Does disabling swap on Linux entirely effectively do the same thing as calling mlock on every bit of memory? Well, I know the kernel treats it very differently, but the effect, I'm saying effectively. What mlock actually guarantees, pages are pinned, they cannot be reclaimed by the kernel. They will not be swapped and will not be dropped. The kernel treats them as unevictable. They stay resident until munlock exit or the mapping is destroyed. Cannot be written to swap. Drop file back pages. So the cache for the file, it's like I can drop those things. So if you're doing file-based I/O, then it can drop the pages for that potentially. I guess what I want to know is, does calling mlock on a region of memory for performance reasons to prevent swap have any benefit on a machine that has swap disabled? There's more than no swap. This is where nuance lives. Even with swap disabled, the kernel can still reclaim memory under pressure. Yeah, but the okay. I don't think it's quite understanding what I'm saying, so I had to narrow it down, and even then it kind of like didn't give me a very clear answer. So either my understanding of this is way incorrect, but the way that I'm understanding is that if you're using mlock to make it sure that a region of virtual memory does not get swapped, if that is your intention of doing the mlock, then if you just have a machine that doesn't have swap, effectively you've done that for the entire computer. That was kind of what I was asking it, and it wanted to go on about killers and stuff like it's like, yeah, dude, like the killer can kill you at any time for any reason. Like, it's like the kernel can do whatever it wants. Anyways, let's see. Another reason for lock, that's okay. Access to lock pages are guaranteed to never be delayed by page fault. This is used for application that must ensure rapid response times. Another reason for locking memory is security. If a virtual memory page contains sensitive data, is never swapped out, then no copy of the page is ever written to the disk. Again, if you don't have a swap disk, then no problem. If the page was written to disk, I want to see here. Give me the shell command to tell what swap space I have on my machine, my Linux machine. Free-h. Does that have 4 gigs of swap? And then if I say mount, maybe if I do CF disk on, what's root here? What is this? Dev mapper root. CF-L, I think it is. ls-la dev grep sd nvme. Okay, we'll do nvme 0. Dev nvme 0. So I do have 2 partitions. This is a character device, so this is for the controller, I think. I think this is actual the block device for the disk. So I want to do n1 sudo. Oh. Okay. So I have this partition 1, which is for the EFI system boot, and then I have Linux root. Swap on show. Dev ZRAM partition 4 gigs. So then if I mount grep for ZRAM 0, it's not even there. Grep swap total proc mem info. df-h grep swap. What was the other one? Free-h. I don't see a partition that is 4 gigabytes for dedicated for swap. Where would this swap actually be stored? Tell me how to find out. Back in the day, I used to have a dedicated swap partition. But I guess on modern Linux it's very often a swap file, not a dedicated partition. So swap on show. It says it's type partition though. Compressed RAM based block device. Stored in RAM, compressed, not on disk, very fast. Used as a pressure valve, not a persistence mechanism. But it says partition, even though it says no swap partition. Hey, ls block, man ls block, list block devices, nice. LSBLK, I like this. So we got our ZRAM disk, which is of 4 gigs of RAM. Dedicated for swapping. Why would you swap? I guess the idea is that, like, okay, say you had all zeros for your page. Well, if you gzip that, that's just like storing it as an integer. It's like a small integer. You don't have to store the entire page as zeros. So I guess that would allow you to like swap those things out into a compressed format, but still be in RAM so that it's not too costly going out to a disk. That's pretty cool. And then you got NVMe 0 and 1. Again, that's the block device. NVMe 0 would be the character device. And then the 2 partitions, EFI takes up 2 gigs. And then the second gig is a encrypted partition that has all the other stuff in it. Alright, sounds good. Sorry, I just wanted to like explore a few little things about my computer there. It's been a while since I've like done Linux as a workstation, so this gives me an opportunity to explore some of those things. All right. An attacker could deliberately engineer the situation by running a program that consumes a large amount of memory, thus forcing the memory of the other process to be swapped out to disk. Reading information from a swap space could even be done after the process has terminated, since the kernel makes no guarantees about zeroing out data held in swap space. Normally, only privileged processes would be able to read from the swap device. The suspend mode on laptop computers, as well as some desktop systems, saves a copy of system's RAM to disk regardless of memory locks. In this section, we look at the system calls used for locking and unlocking part or all of a process's virtual memory. However, before doing this, we first look at a resource limit that governs memory locking. Okay. R-limit memlock resource limit. In section 36.3, we briefly describe the R-limit memlock limit, which defines a limit on the number of bytes that a process can lock in memory. We now consider this limit in more detail. In Linux kernels before 2.6.9, on privileged process IPC lock can lock memory, and the R-limit memlock soft resource limit places the upper limit. And the R-limit memlock soft resource limit places an upper limit on the number of bytes that a privileged process can lock. Starting with Linux 2.6.9, changes to the memory locking model allow unprivileged processes to lock small amounts of memory. This is useful for an application that needs to place a small piece of sensitive information in locked memory in order to ensure that it is never written to the swap space on disk. For example, GPT does this with passphrases. As a result of these changes, no limits are placed on the amount of memory that a privileged process can lock. No limits are placed on the amount of memory that a privileged process can lock, i.e. R-limit lock is ignored. An unprivileged process is now able to lock memory up to a soft limit defined by the R-limit memlock. The default value for both the soft and hard limit R-limit memlock limits is 8 pages. The R-limit memlock, try doing getconf on R-limit memlock. ulimits -l. Oops. Okay. There we go. 8 megs. Okay, let's start from here. Since virtual memory is managed in units of pages, memory locks apply to complete pages. When performing limit checks, the R-limit memlock limit is rounded down to the nearest multiple of system page size. Although this resource limit has a single soft value, in effect, it defines 2 separate limits. For mlock, mlock-all, and the mmap, mlock operation, R-limit memlock defines a per process limit on the number of bytes of its virtual address space that a process may lock. For shared memory CTL, SHM lock operation, R-limit mlock defines a per user limit on the number of bytes in shared memory segments that may be locked by the real user ID of the process. When a process performs a shared SHM CTL lock operation, the kernel checks the total number of bytes of system V shared memory that are already recorded as being locked by the real user ID of the calling process. If the size of the to be locked segment would not push that total over the process memlock limit, the operation succeeds. So basically it's like a global limit as well, because of the system V shared memory is a global namespace. Or global kernel space that needs to have accounting applied to it instead of process specific. The reason R-limit memlock has different semantics for system V shared memory is that the shared memory segment can continue to exist even when it's not attached by any process. It is removed only after an explicit RMID operation, and then only after all processes have detached it from their address space. Locking and unlocking memory regions. A process can use mlock and mlock to lock and unlock memory regions of memory. You just say, hey, this is the area I want to lock or unlock, and this is the length. Similar to the API of mprotect, except there's no prot argument here. The mlock system call, sorry, I'm on the, right here. The mlock system call locks all the pages of the calling process virtual range, starting at adder and continuing for length bytes. Unlike the corresponding argument passed to several other memory-related system calls, adder does not need to be page-aligned. The kernel locks pages starting at the next page boundary below adder. However, SUSV3 option allows an implementation to require that adder be multiple system pages, and portable applications should ensure that this is so when calling mlock and unlock. Because locking is done in units of whole pages, the end of the locked region is the next page boundary greater than length after length plus adder. For example, on a system where the page size is 4096 bytes, the call mlock 2000 4000 will lock bytes 0 through 8191. Okay, that makes sense, yeah. We can find out how much memory a process currently has locked by inspecting the VM lock entry in the link specific proc pin status file. After a successful lock, mlock call, all the pages in the specified range are guaranteed to be locked and resident in physical memory. The mlock system call fails if there is insufficient physical memory to lock all of the requested pages, or if the request violates the mlock soft resource limit. We show an example of the use of mlock in listing 52. The munlock system call performs the converse of mlock, removing a memory lock previously established by the calling process. The adder and length arguments are interpreted in the same way as for mlock. Unlocking a set of pages doesn't guarantee that the CCB memory resident pages are removed from RAM only in response to memory demands by other processes. Aside from the explicit use of munlock, memory locks are automatically removed in the following circumstances: on process termination, if the lock pages are unmapped via munmap, or if the lock pages are overlaid using the map fixed flag. details of the semantics of memory locking, and then finally locking and unlocking all of the process memory. Just disable swapping. You're good. Why do companies disable all swap space? What reference online articles that might have informed this decision? Kind of curious what motivated that decision to disable. So I understand the performance benefits of it. But like this situation where like the machine uses like a gzip compressed region of memory for swapping. I mean, there's going to be a tiny bit of performance overhead, but the gain that you get in like reducing memory pressure on the system without having to kill stuff, kind of like, it might be worth it. I want to come back to this at some point. I'm going to hide this somewhere. I'll put you down here, hide that, make this really small, and I'll come back to this later. Actually, I should put it up here, make this guy small. Cool. All right, where are we at? Details of the semantics of memory locking. In the following paragraphs, we note some details of the semantics of memory locks. Memory locks are not inherited by a child created via fork. Look how far I am into the book here. It's insane. Memory locks are not inherited by a child created via fork and are not preserved across an exec. Where multiple processes share a set of pages, shared mappings, these pages remain locked in memory as long as at least one of the processes holds a memory lock on the pages. Memory locks don't nest for a single process. If a process repeatedly calls mlock on a certain virtual address range, only one lock is established, and this lock will be removed by a single call to munlock. On the other hand, if we use mmap to map the same set of pages, i.e. the same file, at several different locations within a single process, and then call lock on each of these mappings, the page remains locked in RAM until all the mappings have been unlocked. The fact that memory locks are performed in units of pages and can't be nested means that it isn't logically correct to independently apply mlock and munlock calls to different data structures on the same virtual page. For example, suppose we had two data structures within the same virtual memory page pointed to by pointers P1 and P2, and we make the following calls: mlock P1, mlock P2, munlock P1. So now they're both unlocked. All the above calls will succeed, but at the end of the sequence, the entire page is unlocked. That is, the data structure pointed to M2 is not locked into memory. Note that the semantics of the SHM CTL SHM lock operation differ from those of mlock and mlock all as follows. After SHM lock operations, pages are locked into memory only if they are faulted in by subsequent references. That's right. By contrast, mlock and mlock all fault all of the pages, lock pages into memory before the call returns. SHM lock operation sets a property of shared memory segment rather than the process. For this reason, the value in the proc PID status VM lock field doesn't include the size of any attached system V shared memory segments that have been locked using SHM lock. This means that once faulted into memory, the pages remain resident even if all processes detach the shared memory segment. By contrast, a region locked into memory using mlock or mlock all remains locked only as long as at least one process holds a lock on the region. Locking and unlocking all of the process memory. A process can use mlock all and munlock all to lock and unlock all of its memory. Makes sense. This one gets a set of flags, which we didn't get in our individual calls. Our mlock and munlock. The mlock all system call locks all the currently mapped pages into process virtual address space. All the pages mapped in the future or both according to the flag's bit mask, which is specified by ordering together one or both of the following. Current and future. Current lock all pages that are currently mapped into calling process virtual address space. This includes all pages currently allocated to the program text, data segments, memory mappings in the stack. After successful call specifying the current flag, all of the pages of the call process are guaranteed to be memory resident. This flag doesn't affect pages that are subsequently allocated in the process's virtual address space. For this, we must use MCL future. MCL future lock all pages subsequently mapped into the calling process virtual address space. Such pages may, for example, be part of shared memory region mapped via mmap or SHMAT attach, or part of the upwardly growing heap or downwardly growing stack. As a consequence of specifying the future flag, a later memory allocation operation, mmap, sbork, or malloc may fail, or stack growth may yield a 6V signal if the system runs out of RAM to allocate to the process, or the R-limit memlock soft resource limit is encountered. Same rules regarding the constraints, lifetime, and inheritance of memory locks created with mlock also apply for memory locks created via mlock all. The munlock all system call unlocks all of the pages for the calling process, and none does the effect of previous mlock all future call. As with munlock, unlock pages are not guaranteed to be removed from RAM by this call. Before Linux 269 privilege, IPC lock was required to call munlock all, and inconsistently, privilege was not required for munlock. Since Linux 269, privilege is no longer required. Determining memory residence. Okay, so now we're moving on to a different concept, which is memory residence, and determining it. And then we got the advise, and then we're done with this chapter. This is a pretty small chapter, really. I think what I might do is just read through the rest of this chapter and then take a quick break to get some more water. Yeah, we only got like 5 pages left here, or less. It's kind of like a little interlude that he put here to get this topic out of the way before you go into more IPC stuff. And I appreciate it, because after the system v IPC stuff, I'm not too eager to tackle the POSIX IPC stuff. Even though I feel like POSIX will be more interesting to me than system v, it's just like a lot of the same concepts all over again. It's like, bro, I already went through this. I understand these things conceptually. All right. All right. Excuse me. All right. Determining memory residence. M in core. M in core system call is the complement to the memory locking system calls. It reports which pages in a virtual address range are currently resident in RAM, and thus won't cause a page fault if accessed. SOSI3 doesn't specify min core. Sorry, I inhaled some of my protein drink. Ugh. Pro tip, do not inhale your protein shake. Alright. So SUSV3 does not specify MinCore. It is available on many but not all Unix implementations. On Linux, MinCore has been available since kernel 2.4. So we got our MinCore, our address, and the length, so that defines a range. And then we have a vector, which is unsigned character pointer. Interesting. Interesting. Okay. Yeah, I got a question for AI here. I'm gonna say, in C, is char always a byte? Yes. Okay. The MinCore system call returns memory residence information about pages in the virtual address range starting at adder and running for length bytes. The address supplied in adder must be page aligned, and since information is returned about whole page's length is effectively rounded up to the next multiple of the system page size. Information about memory residency is returned in vec, which must be an array of length plus page size minus 1 divided by page size bytes. Okay. Length is passed in. Okay. On Linux, vec has the type unsigned char star. On some other Unix implementations, vec has a type char star. The least significant bit of each byte is, what is the difference? And C, what is the difference between unsigned char and char? Oh shit, I didn't know that char can be... I didn't know that. I always treated char as like a synonym for a byte being unsigned between 0 and 255. That's gross. So I'll use unsigned char in the future. Okay. The least significant bit of each byte is set to the corresponding page, set if the corresponding page is memory resident. The setting of the other bits is undefined on most Unix implementations, so portable applications should test only this bit. The information returned by MinCore can change between the time the call is made and the time the elements of vec are checked. The only pages guaranteed to remain memory resident are those locked with mlock and mlock all. Prior to Linux 2.6.2.1, various implementation problems meant that MinCore did not correctly report memory residence information for map private mappings or other nonlinear mappings established using remap file pages. Listing 52 demonstrates the use of mlock in MinCore after allocating and mapping a region of memory using mmap. This program uses mlock to lock the entire region, or otherwise groups of pages at regular intervals. Each of the command line arguments for the program is expressed in terms of pages. The program converts these to bytes as required for the calls to mmap, mlock, and MinCore. Before and after the mlock call, the program uses MinCore to retrieve information about the memory residency of pages in the region and displays this information graphically. Okay, let's take a look at the program. Okay, so actually, I don't really care about this thing. Let's just read the example that they write here. because this is like a capability that I don't see myself ever using. I don't really care about, so I'm not going to read the code. The following shell session shows a sample run of the program listing 52. In this example, we allocate 32 pages, and in each group of 8 pages, we lock 3 consecutive pages. So we allocate 32 pages, and then each group of 8 pages, we lock 3 consecutive pages. So it's going to be 3 and then 5 unlocked. So in the program output, dots represent pages that are not resident memory, and asterisks represent pages that are resident memory. As we can see from the final line of output, 3 out of each group of 8 pages is our memory resident. In this example, we assumed super user privilege so that the program can use mlock. This is not necessary in Linux 269 later if the amount of memory to be locked falls within the limit. And now we get into the advising stuff, which is page and a half. Let's blast through this. The madvise system call is used to improve the performance of an application by informing the kernel about the calling process likely usage of the pages in the range starting at adder and continuing for length bytes. The kernel may use this information to improve the efficiency of I/O performed on file mapping that underlines the pages. See section 49.4 for discussion of file mappings. On Linux, madvise has been available since kernel 2.4. Okay, the value specified adder must be page aligned. The length is effectively rounded up to the next multiple page system page size. The advice argument is one of the following: normal. This is default behavior. Pages are transferred in clusters, a small multiple system page size. This results in some read ahead and read behind. Random. Pages in the region are accessed randomly, so read ahead will yield no benefit. Thus, the kernel should fetch a minimum amount of data on each read. Sequential. Pages in this range will be accessed once sequentially. Thus, the kernel can aggressively read ahead, and pages can be quickly freed after they have been accessed. We'll need read pages in this region. So I guess sequential would be the hint that I should give my program, my cat program, because I'm reading sequentially. And I will never go backwards, not random. I might add that to my cat program. Let's do that. I don't really care that much. We'll need read pages in this region ahead in preparation for feature access. The will need operation has an effect similar to the Linux specific read ahead system call. And the POSIX fadvise will need operation. Don't need. The calling process no longer requires the pages in this region to be memory resident. The precise effect of this flag varies across Unix implementations. We first note the behavior on Linux for a map private region. The map pages are explicitly discarded, which means that the modifications of the pages are lost. Virtual memory address range remains accessible, but the next access to each page will result in the page fault reinitializing the page, either with the contents of the file from which the is mapped, or zeros in the case of anonymous mapping. This can be used as a means of explicitly reinitializing the contents of a map private region. Interesting, I didn't know that. For a map shared region, the kernel may discard modified pages in some circumstances, depending on the architecture. This behavior doesn't occur in x86. Some other Unix implementations also behave in the same way as Linux. However, on some Unix implementations, madv don't need simply informs the kernel that the specified pages can be swapped out if necessary. Portable applications should not rely on the Linux's destructive semantics for don't need. Linux 2.6.16 added 3 non-standard advice values: don't fork, do fork, and remove. Um, Another advice values is hardware poison, soft offline, mergeable, and unmergeable. These values are used in special circumstances and are described in the manual page. Most Unix implementations provide a version of madvise, typically allowing at least the advice constants described above. However, Susp 3 standardized this API under a different name, POSIX madvise, and prefixes the corresponding advice constants with the string POSIX. Thus, the constants are POSIX madvise normal, POSIX madvise random, sequential, will need, don't need. This alternative interface is implemented in glibc by calls to madvise, but it is not available in all Unix implementations. Susp 3 says that POSIX madvise should not affect the semantics of a program. However, the glibc version before 2.6 don't need operation is implemented using madvise don't need, which does affect the semantics of the program as described earlier. The wrapper implements don't need to do nothing, so that does not affect the semantics of the program. So you're basically wasting your time even making the call. Compiler can just delete that line out of your code. Summary. In this chapter, we considered various operations that can be performed on a process's virtual memory. mprotect system call changes the protection of a region of virtual memory. The mlock and mlockall system call locks part of all the process virtual address space respectively into physical memory. Mincore system call reports which pages in the virtual memory region are currently resident in physical memory. The madvise system call and the POSIX madvise function allow a process to advise the kernel about the process's expected patterns of memory use. Exercise. Verify the effective memlock resource limit by writing a program that sets a value for this limit and then attempts to lock more memory than the limit. Write a program to verify the operation of don't need operation for writable private mapping. I'm good on that. Okay, so 51. Let's go down to the bottom here. We're going to say 10:57, and time is 3:31. So it's about an hour for about 12 pages. It's not too bad. What was my goal? My goal is 75 pages a day. So if we do 75 plus 16, because I started at 10:16, I should be hitting 91 today, which will be basically around the end of POSIX queues. I could go into semaphores a little bit too if I wanted to stay up. Do that. Okay. Well, that was a nice little chapter on some operations for virtual memory. Introduction to POSIX IPC. So this will be a fun little chapter. So this is similar to the structure of System V IPC chapters, where it's an intro, queues, semaphores, and shared memory. Intro here is only going to be, what, 5 pages? Yeah. So not a lot here. But I'm going to take a quick break just to get some more water because my mouth is getting dry. So I will be back in a couple minutes here. All right. Actually, I'm gonna go turn my heater off because it's getting kind of toasty in here. All right. Introduction to POSIX IPC. POSIX IPC. So this might be the one bit of POSIX standards that I actually really feel is an improvement. We'll see when I get through it. But most of the POSIX stuff is just like, just tell me what Linux is doing. I don't care about POSIX. So Linux has sysv IPC and POSIX IPC, but did Linux have its own version of IPC before these standards? Process signals, pipes, and files. Wow, Linux added system VIPC in the early to mid 90s. Wow, that was a long time ago. Linux didn't invent a pre-standard IPC suite, but it did invent new IPC mechanisms that are now fundamental. Unix domain sockets, originally BSD, not SysV or POSIX IPC. Linux leaned hard into them, extended them. SCM rights. Credentials, abstract namespace. Yeah, these are the things that are really unique about authenticating pure PID and URD. Pass file descriptors. Signal FD I love. Timer FD I love. I don't think I've encountered event FD yet. Avoid signal hell, yeah. Okay. Let's start. Introduction to POSIX IPC. The POSIX 1B real-time extensions defined a set of IPC mechanisms that are analogous to the System V IPC mechanisms described in chapters 45 and 48. 45 to 48, I should say. One of the POSIX 1B developers' aims was to devise a set of IPC mechanisms that did not suffer the deficiencies of the System V IPC facilities. These IPC mechanisms are collectively referred to as POSIX IPC. The three POSIX IPC mechanisms are as follows. Message queues can be used to pass messages between processes. As with System V message queues, message boundaries are preserved so that readers and writers communicate in units of messages, as opposed to the unlimited byte stream provided by pipes. POSIX message queues permit each message to be assigned a priority, which allows high priority messages to be queued ahead of low priority messages. This provides some of the same functionality that is available via the type field in System V messages. Semaphores permit multiple processes to synchronize their actions. As with System V semaphores, a POSIX semaphore is a kernel-maintained integer whose value is never permitted to go below 0. POSIX semaphores are simpler to use than System V semaphores. They are allocated individually as opposed to System V semaphore sets, and they are operated on individually using two operations that increase and decrease a semaphore's value by 1, as opposed to the ability of the semop system call to atomically add or subtract arbitrary values from multiple semaphores in a System V semaphore set. Shared memory enables multiple processes to share the same region of memory. As with System V shared memory, POSIX shared memory provides fast IPC. Once one process has updated the shared memory, the change is immediately visible to the other process sharing the same region. This chapter provides an overview of the POSIX IPC facilities, focusing on their common features. API overview. So these are the common features across all POSIX IPC facilities. The three POSIX IPC mechanisms have a number of common features. Table 51.1 summarizes their APIs, and we go into the details of their common features in the next few pages. Except for a mention in Table 51.1, in the remainder of this chapter, we'll overlook the fact that POSIX semaphores come in two flavors: named semaphores and unnamed semaphores. Named semaphores are like the other POSIX mechanisms that we described in this chapter. They're identified by a name and are accessible by any process that has suitable permissions on the object. An unnamed semaphore doesn't have an associated identifier. Instead, it is placed in area memory that is shared by a group of processes or by the threads of a single process. We go into the details of both types of semaphores in chapter 53. Summary of programming interfaces for POSIX IPC objects. So, interface. The header files: message queue is mq.h, semaphore is semaphore.h, shared memory is sysman mman.h. Object handle is a message queue type, semaphore is a semaphore t, and shared memory is just a file descriptor. Create open. So we got open and close for semaphores and message queues, unlink. Create open is a SHM open plus an M map, and then an M unmap, and then SHM unlink. Perform IPC is send and receive, semaphores, post, wait, get value, operate on locations in shared region, miscellaneous operations, Set at or get at or notify. Init, destroy, none. Okay. IPC object names. To access a POSIX IPC object, we must have some means of identifying it. The only portable means that Costudying provides to identify a POSIX IPC object is via a name consisting of the initial slash, followed by one or more non-slash characters. For example, /myObject. So, let me fix my camera here. So this tripped me up initially, the /myObject. I thought that this was actually creating the object in root. And I was like, I don't want it created in root. That's like a really bad idea. But it actually puts it under dev. So for message queues, it'd be under dev mq myObject, which I also thought was kind of weird. But I guess it is what it is. Linux and some other implementations, e.g. Solaris, permit this type of portable naming for IPC objects. Okay. On Linux, names for POSIX shared memory and message queue objects are limited to name max characters. For semaphores, the limit is 4 characters or less. Is 4 characters less, since the implementation prepends the string sem to the semaphore name. Susv 3 doesn't prohibit names of a form other than myObject, but says that the semantics of such names are implementation defined. The rules for creating IPC objects on some systems are different. For example, on True64 5.1, IPC object names are created as names within the standard file system, which would be pretty cool if you could do that. And the name is interpreted as an absolute or relative path name. If the caller doesn't have permission to create a file in that directory, then IPC open call fails. This means that unprivileged programs can create names of the form /myObject on True64, since unprivileged users normally can't create files in root directory. Some other implementations have similar implementation-specific rules for the construction of the names given to IPC open calls. Therefore, in portable applications, we should isolate the generation of IPC object names into separate functions or header file that can be tailored for the target implementation. What about on Linux? All I care about is Linux. Creating or opening an IPC object. Each IPC mechanism has an associated open call, mqOpen, semaphore open, or shm open, which is analogous to the traditional Unix open system call for use for files. Given an IPC object name, the IPC open call either creates a new object with the given name, opens that object and returns a handle for it, or opens an existing object and returns a handle for that object. The handle returned by the IPC open call is analogous to a file descriptor returned by a traditional open call system call. It is used in subsequent calls to refer to the object. The type of handle returned by the IPC open call depends on the type of object. For message queues, it's a message queue descriptor, a value of type mqdt. For semaphores, it is a pointer to type semT pointer. For shared memory, it's a file descriptor. All of the IPC open calls permit at least 3 arguments: name, oflag, and mode, as exemplified by the following shm open call: name, oflag, and mode. Yep. These arguments are analogous to the arguments of the traditional open system call. The name argument identifies the object to be created or opened. The oflag argument is a bit mask that can include at least the following flags: create, exclusive. Depending on the type of object, O flag may also include one of the O read only, O write only, or O read write with meaning similar to open. Additional flags are allowed for some IPC mechanisms. The remaining argument mode is a bit mask, specifying the permissions to be placed on a new object. If one is created by the call, i.e. open create was specified and the object did not already exist, the value that may be specified for mode are the same as for files. As with the open system call, the permission mask in mode is masked against the process umask. The ownership and group ownership of a new IPC object are taken from the effective user and group IDs of the process making the IPC open call. To be strictly accurate on Linux, the ownership of a new POSIX IPC object is determined by the process's file system IDs. To be strictly accurate on Linux, the ownership of a new POSIX IPC object is determined by the process's file system. The FSIDs, file system credentials, which normally have the same value as the corresponding effective IDs. On systems where IPC objects systems where IPC objects appear in the standard file system, sus53 permits an implementation to set the group ID of a new IPC object to the group ID of the parent directory. Closing an IPC object. For POSIX message queues and semaphores, there is an IPC close call that indicates that the calling process is finished using the object, and the system may deallocate any resources that were associated with the object for this process. A POSIX shared memory object is closed by unmapping it with munmap. IPC objects are automatically closed if the process terminates or performs an exec. Unless it hands its IPC objects over to the child via fork before it does its own exec. It's not very common that the parent does an exec. I'm kind of curious. Let's ask AI. It's common for a parent process to fork a child and then have the child exec a new program. Are there use cases where instead of the child performing the exec, the parent does the exec and the child remains continues to run the existing program? Oh yeah, we ran into this in daemonization, so that you can exit the parent. I don't know if it would be an exec. It would be more of an exit to orphan the child under the supervisor. Yeah, the shell may exec itself into the final command. I've seen that happen before. That's pretty cool. Please delete French language. Yeah. Did you know that rm-rf/ doesn't work on Illumos? They hard coded it to just exit and fail the system call. I think it's failed the system call. It might just be in the RM program itself. The idea is, why the hell would anyone ever need to delete their root file system recursively, forcefully? Doesn't make sense. But you can still do it on Linux, I'm pretty sure. I don't want to try testing that one out. Alright, so I get the feeling like there's a bunch of legitimate reasons why you might do this, but the coolest one was the hot reload pattern. The process forks a child. The child continues running the old code, handling the request. The parent execs into the new binary, and then once it's up and running, it coordinates with the child to do handoff back to itself. Then the old child then, cleanly exits. And I guess that allows you to maintain the same PID and maintain its ancestry, because if you forked a child and you terminated the parent, the child would get orphaned and would get inherited by PID1, by the init process. So by doing this, you prevent getting orphaned, and you also preserve the PID that you're running at in case you're doing like signal coordination with PIDs or any number of things with PIDs as an identifier. That's pretty cool. Where did we leave off here? I forget. I guess we'll resume from closing. I'm sure we read this already. Closing an IPC object. For POSIX message queues and semaphores, there's an IPC close call that indicates that the calling process has finished using the object, and the system may deallocate any resources that are associated with the object for this process. POSIX shared memory object is closed by unmapping it with munmap. IPC objects are automatically closed if the process terminates or performs an exit. This is what I was thinking about here. That got me on that tangent. IPC object permissions. IPC objects have a permission mask that is the same as for files. Permissions for accessing an IPC object are similar to those of accessing files, except that execute permission has no meaning for IPC objects. Since kernel 2.6.19, Linux supports the use of access control lists for setting the permissions on POSIX shared memory objects and named semaphores. Currently, ACLs are not supported for POSIX message queues. IPC object deletion and object persistence. As with open files, POSIX IPC objects are reference counted. The kernel maintains a count of the number of open references to the object. By comparison with System V IPC objects, this makes it easier for applications to determine when the object can't be safely deleted. Each IPC object has a corresponding unlink call whose operation is analogous to the traditional unlink system call for files. The unlinked call immediately removes the object's name and then destroys the object once all processes cease using it. When the reference count falls to 0. For message queues and semaphores, this means that the object is destroyed after all processes have closed the object. For shared memory, destruction occurs after all processes have unmapped the object using munmap. After the object is unlinked, IPC open calls specify the same object name will refer to a new object or fail if ocreat was not specified. Kind of like a file system. All right. As with system VIPC, POSIX IPC objects have kernel persistence. Oh God, I hate that is the thing. Okay. Once created, an object continues to exist until it is unlinked or the system is shut down. This allows a process to create an object, modify its state, and then exit, leaving the object to be accessed by some process that is started at a later time. Does it have to be kernel persistence though? Can it be like just file system persistence stored on disk? Listing and removing POSIX IPC objects via the command line. System V IPC provides the two commands IPCs and IPCRM for listing and deleting IPC objects. No standard commands are provided to perform the analogous task for POSIX IPC objects. However, on many systems, including Linux, IPC objects are implemented within a real or virtual file system mounted somewhere under the root directory. And the standard ls and rm commands can be used to list and remove IPC objects. Subsp 3 doesn't specify the use of ls and rm for these tasks. The main problem with using these commands is the non-standard nature of POSIX IPC object names and their locations in the file system. On Linux, POSIX IPC objects are contained in virtual file systems mounted under directories that have the sticky bit set. This bit is the restricted deletion flag setting that it means that an unprivileged process can unlink only the IPC objects it owns. Compiling programs that use POSIX IPC on Linux. On Linux, programs employing POSIX message queues and shared memory must be linked with the real-time library librt using the cclrt option. Programs employing POSIX semaphores must be compiled using the ccpthread option. Comparison of System V IPC and POSIX IPC. As you look at the POSIX IPC mechanisms in the following chapters, we'll compare each mechanism against its System V counterpart. Here we consider a few general comparisons for these two types of IPCs. POSIX IPC has the following general advantages when compared to System V IPC. The POSIX IPC interface is simpler than the System V IPC interface. The POSIX IPC model uses the names instead of keys, and the open, close, and unlink functions is more consistent with the traditional Unix file model. POSIX IPC objects are reference counted. This simplifies object deletion because we can unlink a POSIX IPC object knowing that it will be destroyed only when all processes have closed it. However, there is one notable advantage in favor of System V IPC: portability. POSIX IPC is less portable than System V IPC in the following respects. System V IPC is specified in Subsp 3 and supported on nearly every Unix implementation. By contrast, each of the POSIX IPC mechanisms is an optional component of Subsp 3. Some Unix implementations don't support all of the POSIX IPC mechanisms. This situation is reflected in the microcosm on, hit the wrong button, 1062. Reflected in the microcosm on Linux. POSIX shared memory is supported only in kernels 2.4. A full implementation of POSIX semaphores is available only since kernel 2.6, and POSIX message queues are supported only since kernel 2.6.6. Despite the SUSE3 specification for POSIX IPC object names, the various implementations follow different conventions for naming IPC objects. These differences require us to do a little extra work to write portable applications. Various details of POSIX IPCs are not specified in SUSE3. In particular, no commands are specified for displaying and deleting the IPC objects that exist on the system. In many implementations, standard file system commands are used, but the details of the path names used to identify IPC objects vary. Summary. POSIX IPC is the general name given to 3 IPC mechanisms: message queues, semaphores, and shared memory, that were devised by POSIX 1B as alternatives to the analogous System V IPC mechanisms. I wish they just kept the System V stuff, to be honest. Like, why duplicate functionality here? Even if it's better. Like, just like, we have what we have. The POSIX IPC interface is more consistent with the traditional Unix file model. IPC objects are identified by names and managed using open, close, and unlink calls that operate in a manner similar to the analogous file-related system calls, but not exact. They're not the exact. They're not using open, close, and unlink. They're using their own versions of them. POSIX IPC provides an interface that is superior to many respects on the System V IPC interface. However, POSIX IPC is somewhat less portable than System V IPC. Okay, that takes care of that chapter. Let's go ahead and mark these chapters as done. It's chapter 51. We're 11 chapters away, or no, 12 chapters away from completing this. POSIX Introduction to POSIX IPC. So that one's done. And then chapter 52 is POSIX message queues. I'm just going to go ahead and put the rest of these on here because why not? We're almost done with the book now. At first, I didn't want to list out all of the chapters eagerly because I was like, oh, it'd really suck if I did all that work and then I didn't actually read the book. But I actually read up to chapter 52 at least. So I think I'm going to be able to finish this one. So let's go ahead and copy from here, 52. Can I select? That's a bummer. I wish I had like a text select. These are hyperlinks. What if I do a print screen and then do like all of this? Can I then select the text here? I'll just save and then open it. Can I do OCR on this thing? How do I do OCR on this thing? Okay. Word doc, get out of here. I'm going to ask this thing how to do OCR in Linux because how do you basic text OCR on a PNG image in Linux? Tesseract? That's not a thing. Why don't we Pac-Man OCR? Sorry. Okay, it's Tesseract. 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 Pictures. Screenshot 2026. And then we say standard out. Can I say output? No. Error opening data. Please make sure your test data prefix environment variable is set to test data directory. Well, let's try this again. Tesseract. Pictures. Screenshot 26. Standard out. It did a pretty good job. I mean, it's not perfect, but saves me some typing. Alright. Let's go ahead and delete all that. Some of it's like all caps for no reason. So that requires 7 potatoes. So 52 POSIX message queues. POSIX semaphores. POSIX shared memory. File locking. Sockets. Okay. Unix domain. Fundamentals of TCP/IP networks. Internet domains, server design, advanced topics, terminals, alternative I/O models, pseudo terminals. Bam. So if we zoom out here, if we zoom out a little bit more, so that's chapter 1. Still gotta zoom out a little bit more. Alright, because we got D, yeah. So that is my progress. I started on chapter 1 here, all the way down to 51 so far. Pretty good. Pretty good. Get status, get CI, add remaining chapters to readme. And then I wanted to move chapter 2, chapter 02. If we do 4 x in 3 all the way to 9, do echo $x done will give me 3 to 9, and here I can say get mv chapter x to chapter 0x, and then I can just say don't echo. Oh, there was no chapter 8. Okay. Cool. Now they're all padded so that they list correctly. Get CI, rename, direct chapters to have padding. Get show stat. Yeah. Cool. Well, I'm going to go to my log here, and we're going to say 1063. We are at 422. All right, let's go ahead and get started on that. 52, POSIX message queues. Okay, we got a diagram here. That's nice. Give me something to look forward to. Lots of code, which we'll cruise through. Usually the code doesn't take me long to read. All right. Well, let's be 88, 62, 72, 82. So that'd be 26 pages on message queues. And then that might be it for today. Unless I feel like reading into semaphore some. We'll see how I feel at the end of this. POSIX message queues. This chapter describes POSIX message queues, which allow processes to exchange data from the form of messages. POSIX message queues are similar to System V counterparts in that data is exchanged in units of whole messages. However, there are also some notable differences. POSIX message queues are reference counted, A queue that is marked for deletion is removed only after it is closed by all processes that are currently using it. System V message. Each System V message has an integer type, and messages can be selected in a variety of ways using message receive. By contrast, POSIX messages have an associated priority, and messages are always strictly queued, and thus received in priority order. POSIX message queues provide a feature that allows a process to be asynchronously notified when a message is available on the queue. Hopefully it's a file descriptor, so it's compatible with epoll and select and all that. POSIX message queues are a relatively recent addition to Linux. Recent, I mean, it's been 16 years since this book was published, so not very recent by my standards. The required implementation support was added to kernel 2.6.6 in addition to glibc 2.3.4 or later is required. POSIX message queue support is an optional kernel component that is configured via config POSIX mq option. Doot, doot, doot. I'm going to push my table back here. Overview. The main functions of the POSIX message queue API are the following. Message queue open. Function creates a new message queue or opens an existing queue, returning a message queue descriptor for use in later calls. Message queue send function writes a message to a queue. Message queue receive function reads a message from a queue. Message queue close function closes a message queue that the process previously opened. Message queue unlink function removes a message name, queue name, and marks the queue for deletion when all processes have closed it. The above functions all serve fairly obvious purposes. In addition, a couple of features are peculiar on the POSIX message queue API. Each message queue has an associated set of attributes. Some of these attributes can be set when the queue is created or opened using mqopen. Two functions are provided to retrieve and change queue attributes: message queue getAttr and message queue setAttr. Let me reread this because I wasn't paying attention to what I was reading. I saw the words, but they didn't go into the brain. They just went straight to my mouth. Each message queue has an associated set of attributes. So this is like the associated data structure and System V. Some of these attributes can be set when the queue is created or opened using mqopen. Two functions are provided to receive and change queue attributes: message queue getAttr and message queue setAttr. The message queue notify function allows a process to register for message notification from a queue. After registering, the process is notified of the availability of a message by delivery of a signal or by the invocation of a function in a separate thread. That's a bummer. I guess the signal could then be handled by the signal FD to get a file descriptor, so that's not the end of the world. Just mask it and then have signal FT notify you. Opening, closing, and unlinking a message queue. In this section, we look at the functions used to open, close, and remove messages from or remove message queues. Opening a message queue. mqopen function creates a new message queue or opens an existing queue. Getting through this is going to be painful because it's basically identical to the System V stuff. This is going to be so painful. I don't want to do this. Okay, well, we say, hey, mqopen, and MQOpen is not a system call. If I man up MQOpen, that's a library call. And if I rip grep for MQOpen, my example program measure POSIX message queues, if we go into there, 43, and I build, let's go ahead and make it again. And then I build measure POSIX message queues. There's some protest or something going on outside. I don't know. People are making a ruckus. All right, so if I run strace on this, strace c MQOpen is a system call. Man2 MQOpen. It goes to 3. If I go to man syscalls MQOpen, it's definitely a the MQ library function is implemented on top of a system call of the same name. The library function performs a check that the name starts with a slash, given the invalid error. If it does not, the kernel system call expects name to contain no preceding slash. So C library function passes name without the preceding slash. Name plus 1 to the system call. That's interesting. I guess that's for portability. I don't like it. I'd rather just call the system call. But it doesn't look like they give you access to the system call. Okay. So we got this MQOpen. It takes in the name, which requires it to have a slash in front of it for some silly reason. And then we got our O flag, which are open flags. And then we got a mode, which is optional, because if we're not creating it with the O create, you have to give the mode. And then we have a struct MQAdder, which is a bunch of attributes for the message queue, which is also optional. The name argument identifies the message queue and is specified according to the rules given in section 521.1. The O flag argument is a bit mask that controls various aspects of the operation of MQOpen. The values that can be included in the mask are summarized in table 52.1. Boop. O create. I'm not going to go over these. These are obvious. One of the purposes of the O flag argument is to determine whether we are opening an existing queue or creating and opening a new queue. The O flag doesn't include O create. If O flag doesn't include O create, we are opening an existing queue. If O flag includes O create, a new empty queue is created if one of the given name doesn't or exists. If O flag specifies both O create and O exclusive, and a queue of the given name or exists, then open fails. The O flag argument also indicates a kind of access that the calling process will make to the message queue, specifying exactly one of the values read-only, read-write-only, or read-write. The remaining flag value, non-block, causes the queue to be opened in non-blocking mode If a subsequent call to message receive or message send can't be performed without blocking, the call will fail immediately with the error E again. If MQOpen is being used to open an existing message queue, the call requires only 2 arguments. However, if OCreate is specified in flags, 2 further arguments are required, the mode and the adder. If the queue specified by name already exists, these 2 arguments are ignored. These arguments are as follows. The mode argument is a bit mask that specifies the permissions to be placed on the new message queue. The bit values that may be specified are the same as for files, and as with open, the value in mode is masked against the process umask. To read from a queue, read permission must be granted to the corresponding class of user. To write to a queue, write permission is required. The adder argument is an MQ adder structure that specifies attributes for the new message queue. If adder is null, the queue is created with implementation to find default attributes. We described the MQ adder structure in section 52.4. Upon successful completion, MQOpen returns a message queue descriptor, a value of type MQDT, which is used in subsequent calls to refer to this open message queue. The only stipulations that Subsidy3 makes about this data type is that they may not be an array, that is guaranteed to be a type that can be used in an assignment statement or passed by value as a function argument. On Linux, MQDT is an int, but for example on Solaris it's defined as a void star. An example of the use of MQOpen is provided in listing 52.2. Effective fork, exec, and process termination of message queue descriptors. During fork, the child process receives copies of parent's message queue descriptors. These descriptors refer to the same open message queue descriptions. We explain message queue descriptions in section 52.3. The child doesn't inherit any of its parent's message notification registrations. When a process performs an exec or terminates, all of its open message queue descriptors are closed. As a consequence of closing its message queue descriptors, all of the process message notification registrations on the corresponding queues are deregistered. Closing a message queue. The MQClose function closes the message queue descriptor MQDES. If the calling process has registered via MQDES for message notification from the queue, then the notification registration is automatically removed, and another process can subsequently register for message notification from the queue. A message queue descriptor is automatically closed when a process terminates or calls exec. As with file descriptors, we should explicitly close message queue descriptors that are no longer required in order to prevent a process from running out of message queue descriptors. As with close for files, closing a message queue doesn't delete it. For that purpose, we need MQUnlink, which is a message queue analog to unlink. Removing a message queue. The MQUnlink function removes the message queue identified by name and marks the queue to be destroyed once all processes cease using it. This may mean immediately if all processes had the queue open have already closed it. Okay, we got a little test program here that just calls a link. Nothing incredibly spectacular there. Relationship between descriptors and message queues. So similar to file descriptors. The relationship between a message queue descriptor and an open message queue is analogous to the relationship between a file descriptor and an open file. A message queue descriptor is a per process handle that refers to an entry in a system-wide table of open message queue descriptions. And this entry, in turn, refers to a message queue object. This relationship is illustrated by 52.1. So it's kind of like the inode message queue table. It's kind of like the inode table for the device. On Linux, PostGIS message queues are implemented as inodes. Oh, cool. In a virtual file system, and message queue descriptors in open message. So that means that I should have a mount for that virtual file system, right? If I do mount grep msg, let me just look at the mount. Pipe that into less. Dev. There's dev shm and dev mq. Dev mq is an mq type. Dev mq. Hey, we don't have anything there. But if I run my program, build, measure, POSIX MQ, and I do 1,000 or 10,000 of 1 100, 1 million, and like, oops, I need to do more than that. And I kill it halfway. A CD back to here. It's in the virtual file system. However, these are implementation details that are not required by SUSV3 and don't hold true on some other Unix implementations. Nevertheless, we return to this point in section 52.7 because Linux provides some non-standard features that are made possible by this implementation. Figure 52.1 helps clarify a number of details of the use of message queue descriptors, all of which are now analogs to the use of file descriptors. Let's go back to that diagram. So you have process A with message queue descriptor table, and it has the other info. So it's kind of like the flags on the file descriptor. And then these are open message queue descriptions, which are kind of like the flags and the pointer for the file description. And then the message queue table is kind of like the inode table per device. This is per queue info. And usually inodes have most of the stuff. This is for like seek. So I imagine this would be things. Yeah, I don't know. I don't know what would go in there other than flags. Alright, let's continue over here. An open message queue description has an associated set of flags. SUSV3 specifies only one such flag, which is non-block, which determines whether IO is non-blocking. Two processes can hold message queue descriptors, descriptor X in the diagram, that refers to the same open message queue description. This can occur because a process opens a message queue and then calls fork. These descriptors share the state of the O non-block flag. Two processors can hold open message queues descriptors that refer to different message queue descriptions that refer to the same message queue. E.g., descriptor Z in process A and descriptor Y in process B both refer to /MQR. This occurs because two processes each use MQ to open the same queue. So it was Z. What are we talking about here? Z in process A and Y in process B. Yeah, MQR. Message queue attributes. The MQ open, MQ get adder, and MQ set adder functions all permit an argument that is a pointer to an MQ adder structure. The structure is defined in MQH as follows. Flags, max message, message size, current messages. Before we look at the MQ adder structure in detail, it's worth noting the following points. Only some of the fields are used by each of these three functions. The fields used by each of these functions are indicated in the comments accompanying the structure definition above. The structure contains information about open message queue description, associated flags associated with message queue descriptors, and information about the queue referred to by that descriptor. Some fields contain information that is fixed at the time the queue is created, and others return information about the current state of the message queue description or message queue. Setting message queue attributes during queue creation. When we create a message queue with MQ open, the following MQ adder fields determine the attributes of the queue. MQ max message field defines the limit on the number of messages that can be placed on the queue using MQ send. This value must be greater than 0. The MQ message size field defines the upper limit on the size of each message that may be placed on the queue. This value must be greater than 0. Together, these two values allow kernel to determine the maximum amount of memory that this message queue may require. The message queue max message and message queue's max size attributes are fixed when the message queue is created. They can't subsequently be changed. In section 52.8, we describe two proc files that place system-wide limits on the values that can be specified for the max message and message size attributes. The program in listing 52.2 provides a command line interface to the open function that shows how the adder structure is used with open. Two command line options allow message queue attributes to be specified. -M for max message and -S for size. If either of these options is supplied, then a null adder p argument is passed to open. Some default values are assigned to the fields of the adder structure in which adder points in case of one of the M and S options is specified on the command line. If neither of these options is supplied, adder P is specified as null when calling open, in which case queue will be created with the implementation defined defaults for the queue attributes. I don't really care about this program. Retrieving message queue attributes. It's gonna be just reading those values. I don't really need to read those. Let's read the shell session, I guess. In the following shell session, we use the program listing 52.2 to create a message queue with implementation defined default attributes, and then use the program in listing 52.3 to display the queue attributes so that we can see the default settings on Linux. Bam. So we say I'm going to create with exclusive my MQ, and I'm going to get adder. It's going to say, hey, I got a maximum number of messages 10, maximum size is 8K, and then there's 0 currently on the queue, and then I'm going to link it. From the above output, we see that the Linux default values for MQ max message and size are 10 and 8K respectively. There is a wide variation in implementation defined defaults for max message and message size. Portable applications generally need to choose explicit values for these attributes rather than relying on the defaults. Modifying these attributes, so you got a set adder function that takes in the descriptor and then takes in the new adder and then gives you back the old adder. I'm not gonna go into detail on that API. It's pretty straightforward. Exchanging messages, sending messages, receiving messages, sending and receiving messages with a timeout. I don't really feel like reading all this stuff. As noted at the beginning of the chapter, the type attribute of systemd messages provides a different functionality. Systemd messages are always queued in FIFO order, but message receive allows us to select messages in various ways. in FIFO order by exact type or by highest type less than or equal to some value. All right, well, let's read it just because it has some information about priorities in here that might be useful. The MQ send function adds the message in the buffer pointed to by message PTR to the message queue referred to by the descriptor MQDES. The message len argument specifies the length of the message pointed to by the PTR. This value must be less than or equal to, yeah, obviously, otherwise send fails. Obviously, each message has a non-negative integer priority specified by the message prior argument. Messages are ordered within the queue in descending order of priority. When a new message is added to the queue, it is placed after any other messages of the same priority. If an application doesn't need to use message priorities, it is sufficient to always specify prio as 0. Susy 3 allows an implementation to advertise its upper limit for message priorities, either by defining the constant prio max, blah, blah, blah. I don't care about any of this. If the message queue is already full, then further sends either blocks until spaces becomes available, or if you have the O non-block flag, it fails immediately with the E again. Pretty typical what you expect. The program will, in listing 52.4, provides a command line interface to the message queue send function. We demonstrate the use of this program in the next section. Don't really care. Receiving message. The receive function removes the oldest message from the highest priority from the message queue referred to by MQDES and returns that message in the buffer pointed to by message PTR. Message queue receive. Pretty straightforward. The length is obvious, pointer is obvious. Regards to the actual size of the message length and thus the size of buffer pointed to by PTR must be greater than or equal to the message size attribute of the queue. Otherwise, the receive fails with the error eMessage size. If we don't know the value of the message queue size attribute of the queue, we can obtain it using getAttr. In the application consisting of cooperating processes, the use of getAttr can usually be dispensed with because the application can typically decide on the message queue's size in advance. If message priority is not null, then the priority of the received message is copied into the location pointed to by message priority. That's helpful. If the message queue is currently empty, then MQ receive either blocks until a message becomes available, or if the O non-block flag is in effect, fails immediately with E again. Pretty typical. There's no equivalent of the pipe behavior where the reader sees end of file if there is no writers. So we don't know when to clean up. The writer could just go away, and then we're all just like sitting here reading, waiting for the writer, and not knowing that he's gone away. The program listing 52.5 provides a command line interface to the receive function. The command line format program shown. Yeah, okay. Yeah. The following shell session demonstrates the. Oops, sorry, I'm on the wrong page here. The following shell session demonstrates the use of the program listing 52.4 and listing 52.5. We begin by creating a message queue and sending a few messages with different priorities. So we say, hey, message A with priority 5, message B with priority 0, message C with priority 10. We then get back C first because it has the highest priority. And then 5, and then message B is last. As you can see from the above output, the messages were received in order of priority. At this point, the queue is now empty. When we perform another blocking receive, the operation blocks. Boop, 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 boop. On the other hand, if we perform a non-blocking receive, the call returns immediately with the failure status. Yeah, because there's no one to wait for. No messages in the queue. All right, I'm not going to read that. So one thing I just thought of is that why would you use like a message queue built into the kernel versus using a message queue in the process's memory? And when it comes to like a reliability perspective, if you can get it into the kernel, then at least kernel memory is going to persist any individual process crashing. Obviously, if the kernel crashes or if the kernel restarts, then the message queue is going to die. That's just how it works, I'm pretty sure. Can ask AI here, but I'm pretty sure that's what happens. With POSIX message queues and the dev, what do you call it? Dev MQ virtual file system. If I have stuff in a queue, say dev mq foo, and I restart the program, the kernel, the computer, will that queue be deleted? Yep, it'll be gone, exactly. So moving stuff into a queue that's in the kernel at least gives you some level of protection against process crashes, if that is a concern. But it's not going to protect you against system crashes or restarts, or power outages, or any sort of things. So what a lot of people do is they put things into queues on the network, and they consider that safe because it's better that it's in the network somewhere than on a machine that might crash. Because when you send it to a network system, those systems can have certain guarantees around durability, about writing things to disk, so that if there is a crash, they're resilient to it. Okay. So we are at 1077, and this chapter wraps up at 1087. So we're about 10 pages off. It's about 5 p.m. And I think that'll be our goal for the day. 1087. It's about 5 or 7 pages, something like that, off. If we do 87 minus 16, it's only 71, so we're 4 pages off from our goal. Isn't that the end of the world? But I might just take a break there at the end of this chapter, and because the next chapter is just, I might just bulldoze my way through semaphores, because it's just going to be more of the same system V semaphore stuff. This might be different and unique. This I don't really, I'm interested in it, but I'm not super interested in it. And then we get into sockets. Wow. Introduction, Unix domain sockets, fundamentals of TCP sockets, inner domains. Server design, advanced topics, send file, bam, my favorite. Then we have a section on terminals, alternative IO models, and then pseudo-terminals, and then we're done. So this is going to be a banger right here, alternative IO models. And then we got a bunch of socket stuff, which is great. So I might try to get to the end of semaphores today, or at least partially into it. I don't know, we'll see. I think I'm going to take a break at message queues, get dinner, relax, and if I feel like hopping on again for like an hour, maybe do another hour on semaphores. Before I do that though, let me check some stuff here on Discord. Sending and receiving messages with a timeout. The MQ timed send and MQ timed receive functions are exactly like MQ send and receive, except that if the operation can't be performed immediately and the non-block flag is not in effect for the message queue description, then the abs timeout argument specifies a limit on the time which the call will block. Pretty straightforward. The abs timeout argument is a time spec structure that specifies a timeout as an absolute value in seconds and nanoseconds since the epoch. So it says at this time in the future, stop. To perform a relative timeout, we can fetch the current value of the clock real-time clock using clock get time and add the required amount to that value to produce a suitably initialized time spec structure. If a call to MQ timed send or MQ timed receive times out without being able to complete its operation, then the call fails with the error E timed out. On Linux, specifying abs timeout as null means an infinite timeout. However, this behavior is not specified in SUSP3 and portable applications can't rely on it. The MQ timed send and MQ timed receive functions originally derived from POSIX 1D 1999 and are not available in all Unix implementations. Message notification. A feature that distinguishes pushes message queues from their system V counterparts is the ability to receive asynchronous notification of the availability of a message on a previously empty queue, i.e. when queue transitions from being empty to non-empty. This feature means that instead of making a blocking MQ receive call or making the message queue descriptor non-blocking and perform periodic message queue receive polls on the queue, a process can request a notification of message arrival and then performs other tasks until it is notified. The process can choose to be notified either via signal or via invocation of a function in a separate thread. Oh, that's cool. You can say in a different thread. I like that. I'd rather have that than the signal. The notification feature of POSIX message queues is similar to the notification facility that we described for POSIX timers in section 23.6. Both of these APIs originate in POSIX 1b. The MQ notify function registers the calling process to receive a notification when a message arrives on the empty queue referred to by the descriptor MQDES. And we give it this SIG event notification structure, which I'm sure we'll get into, that describes exactly how to do that. And that'll take up a bunch of discussion here and code examples. Then we get into Linux specific features, and then we have a discussion about limits and summary. Okay, not much left here. The notification argument specifies the mechanism by which the process is to be notified. Before going into the details of the notification argument, we note a few points about message notification. At any time, only one process, the register process, can be registered to receive a notification from a particular message queue. If there's already a process registered for a message queue, further attempts to register that queue fail. MQ notify fails with the error eBusy. That's a bummer. You can have multiple clients waiting on the queue, and you want them all to wake up. I guess you can't do that. Bummer. The registered process is notified only when a new message arrives on a queue that was previously empty. If a queue already contains a message at the time of the registration, notification will only occur after a queue is emptied and a new message arrives. After one notification is sent to the register process, the registration is removed, and any process can then register itself for notification. In other words, as long as a process wishes to keep receiving notifications, it must re-register itself after each notification by once again calling MQ notify. The register process is notified only if some other process is not currently blocked in a call to MQ receive for the queue. If some other process is blocked in MQ receive, that process will read the message and the register process will remain registered. A process can explicitly deregister itself as the target for the message notification by calling MQ notify with a notification argument of null. We already showed the SIG event structure that is used to type the notification argument in section 23.6.1. Here we present the structure in simplified form, showing just those fields relevant to the discussion of MQ notify. So we got our union sigval, which is a integer for the signal or a sigval pointer. So that's like when you're doing a real-time signal, you can send that little integer along. And then we got our sig event, which is a notify, a signal no. So the method, the notification signal, the value for the signal, and then the function if it's a thread notification, which just receives a signal value, and then finally some attributes. Okay, The SIGEV notify field of this structure sets one of the following values. None. Registers process for notification, but when the message arrives on the previously empty queue, don't actually notify the process. As usual, the registration is removed when the new process arrives on empty queue. I don't understand the point of that. Because you can deregister with null. You don't need to pass in a none. Not sure how that's useful. Signal. Notify the process by generating the signal specified in the SIGEV signo field. The SIGEV value specified data to accompany the signal. The data can be retrieved via the SI value field of the SIGINFO T structure that is passed to signal handler or returned by the call to SIGWAITINFO or SIGTIMEWAIT. The following fields in the SIGINFO T structure are also filled in SI code with the value SI message queue, SI signo with the signal number, SI PID with the process ID of the process that sent the message, and SI UID with the real user ID of the process that sent the message. SIGEV thread, notify the process by calling the function specified in SIGEV notify functions as if it were a start function of a new thread. The SIGEV notify attributes field can be specified as null or as a pointer to a pthread adder structure that defines attributes for the thread. The union SIGVAL value specified as the SIGEV value is passed as the argument of this function. Receiving notification via signal. Listing 52.6 provides an example of message notification using signals. This program performs the following steps. I'm not going to go over the textual explanation. I will look at the code. So here we do our open, adder, malloc for a message. We set up our signal handler, our mask, our signal handler. We set up our notify structure. And then forever, we sig suspend. We do our MQ notify up here. Okay. Various aspects of the program in listing 52.6 merit further comment. We block the notification signal and use sig suspend to wait for it, rather than pause to prevent the possibility of missing a signal that is delivered while the program is executing elsewhere. i.e. is not blocked waiting for signals. In the for loop, if this occurred and we were using pause to wait for signals, then the next call to pause would block, even though the signal had already been delivered. We open the queue in non-blocking mode, and whenever a notification occurs, we use the while loop to read all messages from the queue. Emptying the queue in this way ensures that all further notifications is generated when a new message arrives. Employing non-blocking mode means that the while loop will terminate when we have emptied the queue. This approach is analogous to the use of non-blocking I/O with edge-triggered I/O notifications, which we'll describe in section 63.1.1, and is employed for similar reasons. Within the for loop, it is important that we re-register for message notification before reading all messages from the queue. If we reverse these steps, the following sequence could occur. All messages could be read for the queue, and then the while loop terminates, and the message placed on the queue is called to re-register for message notifications. At this point, no further notification signal would be generated because the queue is already non-empty. Consequently, the program would remain permanently blocked in its next call to SIG suspend. Yeah. Receiving notifications via thread. Listing 52.7 provides an example of message notification using threads. This program shares a number of design features with 52.6. When a message notification occurs, the program re-enables notification before draining the queue. Non-blocking mode is employed so that after receiving notification, we can completely drain the queue without blocking. So here we have our own dedicated thread func and notify setup. So here we have our message queue descriptor that we get from opening and non-blocking mode, and then we notify setup. Notify setup then sets up our notify situation to be a thread, gives it the thread func, and then say, hey, notify me when it's 0. Because we haven't put anything on the queue yet, it's 0, so this thing gets notified. I don't think it has a transition to non-0 and then back to 0. But regardless, this thing will get notified when it hits 0. And then when that happens, this thing's going to read its attributes into adder. Adder is then used to allocate a buffer to read into. We then reset up our notification because it got removed when the thread was invoked. So we reset that up. I didn't realize that we were putting the pointer on here. But I guess that's needed so that we can reference the message queue descriptor because they're not using global memory. We're passing it through the notifications. This is where we do our reads, our non-blocking reads, until we no longer can read anything. If it's not E again, then we say, hey, something was wrong. This is not a failure because the queue is at 0. And then we free our buffer and we exit our thread, which I think you can do just by returning from the thread func. I don't think you have to explicitly exit there. Doesn't hurt to be explicit though. Note the following points regarding the design of this program. Listing 52.7, the program requests notifications via thread by specifying SIG EV thread and SIG EV notify field of the SIG event structure passed to notify. The thread start function thread func is specified in the notification function field. After enable message notification, the main program pauses indefinitely. Message notifications are delivered by invocations of thread func in a separate thread. We could have made the message queue descriptor MQD visible to thread func by making a global variable. However, we adopted a different approach to illustrate the alternative. We placed the address of the message queue descriptor in the SIG EV value SIG val pointer field that is passed to MQ notify. When thread func is later invoked, this address is passed as its argument. We must assign a pointer to the message queue descriptor to SIG EV value signal PTR rather than some cast version of the descriptor itself, because other than stipulation that it is not an array type, sus v3 makes no guarantee about the nature of the size and type used to represent the message queue descriptor type. Linux specific features. The Linux implementation of POSIX message queues provides a number of features that are unstandardized but nevertheless useful. Alright, we got the Linux specific stuff, some message queues, comparison between POSIX and System V message queues, and then a summary. Alright. Displaying and deleting message queue object via command line. I wonder if I could do another mount somewhere else. So ls.la media, is that a thing? No. Mount, is that a thing? Okay. Can I do mkdr mount, we'll say mqueue? No, it doesn't like that. What if I do like mkdr-p mnt mqeue? Would that work? And then we say mount type mqeue none, and we say mnt mqeue sudo bang bang. Hey. Nice. It's kind of like TempFS in that way. The source can be any name at all. Oh, sorry. Let's start from the beginning here. In Chapter 51, we mentioned that POSIX IPC objects are implemented as files in virtual file systems, and that these files can be listed and removed with ls and rm. In order to do this with POSIX message queues, we must mount the message queue file system using the command of the following form: mount type mq source target. The source could be any name at all. Specifying the string none is typical. Its only significance is that it appears in proc mounts and is displayed by the mount and df commands. The target is the mount point for the message queue file system. The following shell sessions show how to mount the message queue file system and display its contents. We begin by creating a mount point for the file system and mounting it. Next, we display the record in proc mounts for the new mount, and then display the permissions for the mount directory. One point of note from the output in the ls command is that the message queue file system is automatically mounted with a sticky bit set for the mount directory. I don't see that. Oh yeah, I do. The T. Okay. We see this from the fact that there is a T in the other execute permission bit displayed in ls. This means that an unprivileged process can unlink only message queues that it owns. Next, we create a message queue using ls to show that it is visible in the file system, and then delete the message queue. Obtaining information about a message queue, we can display the contents of the files in the message queue file system. Each of these virtual files contains information about the associated message queue. Oh, you can cat it out. I didn't know that. I didn't know that. Let's cat it out. Isn't that interesting? What if I like write something to it like echo foo into that, or maybe I'll append it. It's like, yeah, you can't do that. dummy. You can't write to it. The queue size is a field of the total number of bytes of data in the queue. The remaining field relate to message. The remaining fields relate to message and notification. The notified PID is non-zero. Then the process with the specified PID has registered for message notification from this queue, and the remaining fields provide information about the kind of notification. Notify is a value corresponding to one of the AV notify constants, 0 for signal, 1 for none, or 2 for thread. And then the notification method is, if the notification method is signal, the signal field indicates which signal is delivered for message notification. Following shell session illustrates the information that appears in these fields. So we registered for notification, and then we show up there with our PID running in the background there. We're going to get signal 10, and then we kill our background job, and then we say, hey, notify thread. Different PID is now registered for the notification. Notify method is now listed as 2. Using message queues with alternative I/O models. This is what I'm interested in. In the Linux implementation, a message queue descriptor is really a file descriptor. We can monitor this file descriptor using I/O multiplexing systems called select and poll, or the epoll API. See chapter 63 for details of these APIs. This allows us to avoid the difficulty that we encounter with system V message queues when trying to wait for input on both message queue and a file descriptor. Refer to section 46.9. However, this feature is non-standard, so SVT doesn't require that message queue descriptors are implemented as file descriptors. Well, that's good. I didn't realize that they're implemented as file descriptors, because the table earlier was like, they're their own type. They're not the same as a file descriptor. But I guess in Linux they are file descriptors, which is nice, which means that you can use them with select, poll, and epoll. But it also means that you don't have to do any of this notification silly stuff, you know? You could just like get the file descriptor and put it into a select and wait for it to have a message sent to it. Message queue limits. SUSE3 defines 2 limits for POSIX message queues. This is all limit stuff. I don't really care about this. Priority max, open max. The only thing I really care about is the comparison of POSIX and System V message queues. Section 51.2 listed various advantages of the POSIX IPC interface over the System V IPC interface. The POSIX IPC interface is simpler and more consistent with the traditional Unix file model. The POSIX IPC objects are reference counted, which simplifies the task of determining when to delete an object. These general advantages also apply to POSIX message queue. POSIX message queues also have the following specific advantages over System V message queues. Message notification feature allows a single process to be asynchronously notified via signal or the instantiation of a thread when a message arrives on a previously empty queue. On Linux, POSIX message queues can be monitored using poll, select, and epoll. System V message queues don't provide this feature. However, POSIX message queues also have some disadvantages compared to System V message queues. POSIX message queues are less portable. This means that this problem applies even across the Linux system, since message queues support is available only. That's not an issue anymore. The facility to select System V messages by type provides slightly greater flexibility than strict priority ordering of POSIX messages. There's a wide variation in the manner in which POSIX message queues are implemented on Unix systems. Some systems provide implementations in user space, and on at least one such implementation, Solaris 10, the MQ Open manual page explicitly notes that the implementation can't be considered secure. On Linux, one of the motives for selecting a kernel implementation of message queues was that it was not deemed possible to provide a secure user space implementation. What does that mean? What does that mean? Let's ask AI. What is meant here by secure? Okay. Summary. POSIX message queues allow a process to exchange data in the form of messages. Each message has an associated integer priority, and messages are queued and thus received in order of priority. POSIX message queues have some advantages over System V message queues, notably that they are reference counted, and that a process can be asynchronously notified in the arrival of messages on an empty queue. However, POSIX message queues are less portable than System V message queues. Not going to do any of these exercises. Done. Boop, boop. Okay. This is page, what? 1089. It's 5:30. 1089 is 5:30. And we are done for the day. Yeah, I'm done for the day. I don't have it in me to read any more of this IPC stuff. So tomorrow we'll get semaphores and shared memory done, and then we'll be done with IPC. And then file locking. So Thursday would be interesting because it would be the introduction to sockets, Unix domain, fundamentals, blah, blah, blah. Server design, all the socket stuff. So Thursday, Friday are going to be interesting. And then alternative IO models. I'm going to spend a lot of time on this stuff. I'm not going to try to rush it. I don't even care if I go into next week. I'm kind of ripping the band-aid off with the IPC stuff because I'm tired of it. But once we get to sockets, I think I'm just going to take my time, go at a reasonable pace, and then finish next week. Yeah. Okay. Well, today I got how many pages read? So if we do 1089 minus 1016, then we got 73, and our goal was 75, so we're not too far off. All right. I think that's going to be it for me tonight. I got some chores I got to do this evening anyways, so all right, yeah, I'll be back on tomorrow morning to resume on POSIX semaphores and finishing up the POSIX IPC stuff, file locking, and then eventually getting into sockets either tomorrow afternoon or Thursday, which will be fun. So, all right, I'll be on tomorrow morning. Yep.